Okay, what we're going to do here is look at a couple things having to do with things on inclined planes. And there's a particular problem that I mentioned at the end of the chapter. That was problem number 27.
Oh, I was going to ask about that one.
Okay, problem 27 is a CHEB. It should be an easy problem. It's only got 2 dots. It's kind of a hard problem. They don't know how to set dots up on those. So if I put something on the hill, and I'm not going to do that problem because we don't have time, but I'm going to set it up for you. This is a video I did for the honors guys. I don't know if I put it on if you go to chapter 6 over on the right-hand side, there might be 3 there now. There might be an honors one. The first one's pretty easy. The second one lets you determine, is it going to move or not? And what we have to do in problem 27 is we have to say, first of all, A, is it going to move? B, which way is it going to move? And if it does move, what's its acceleration? And if it's moving uphill, what's its acceleration? If it's moving downhill, what's its acceleration? So there's no simple little quick trick you can do, like if you don't know which way it goes, you calculate it, you look at the sign on the acceleration. A negative acceleration means it goes the other way. Well, it doesn't work here, because if it doesn't move, you're going to get a negative sign also. So you need a different trick on this. What you do is you do the problem without friction. So then find the direction. Not acceleration, though. That's useless. Because there's no friction, it's not the same problem. Find the direction it's going to move. If you think about it, if you put friction in there, it's either going to move in that direction a little more slowly, or it's not going to move. It's not going to go uphill. Okay, so that's one thing you know. No matter what I do, it's going to either try to go that direction, or it's going to go that direction. It will not go the other direction.
So when you say find the direction, you're solving for the acceleration, but not the number of the sign?
Right. You're solving for the sign of the acceleration, or there's a couple ways you can do it. I showed one way on that honors video where you calculate the down the hill force, the mg sine theta. You just write it down. You say mg sine theta equals, let's say, 5 kilograms times 9.8 meters per second squared times the sine of 15 degrees. And you get a number for this, let's say, 14 newtons or something. And then you calculate the up the hill force, whatever that is. And you compare those two. If the F static max is 17 newtons, he's not going anywhere. If it's 12 newtons, then it's going somewhere. So that's one way to numerically calculate these two things rather than doing F net equals ma, because you don't know what A is. I mean, you can write this, or 0, or up, or down. So this will not help you. If you look at the individual mg sine theta, let's say we guess that it's minus F static equals what? A number. Okay, so you would calculate that force, and then you would calculate this force, I should say, and then you would calculate this force. You could calculate the two together, and if it came out negative, it's obvious that it's not going to move, so you could do that, but you can't really put ma over there because you don't know what it is. And if it's static and it accelerates, then that's sort of a contradiction. So there's various ways to do it. This numerical way, I think, is good because these numbers can be used later on in the problem. So now, the next thing is now we have friction. How's this? My neck hurts. So now, add friction. So let's say that we learned it goes uphill. So what's the modified diagram going to look like? You're going to have your mg sine theta down here. That's an S. You're going to have your tension up here. It should be longer. You're going to have your tension up there. And what else are we going to have in this problem? You have friction pointing which way? down, because this will go uphill without friction. So when we add friction, the friction's going to be saying, no, I don't want you to go up there that much. Now, does it move with that friction? You might have to put F static in here and see what happens, or look at these two numbers and see what happens. So we'll go through that one. We'll dissect that one completely on Monday. Then what happens if it goes downhill? So if it goes downhill, then your free body diagram will always have the same mg sine theta, whether it goes up, down, or even if it doesn't move. We're still going to have the tension, but he's going to be smaller. Where's the friction going to go? He's going to go up. Now, if the friction's big enough, this thing may not be able to move. This stuff together might be too big. If it's smaller than this, then it will go downhill. So you see the pattern you have to use? Does it move? And if so, which direction? No, without friction, which direction does it move? Now, what if things perfectly balanced? You're probably not going to run into that usually. If you put friction in there, it's just going to stay perfectly balanced. But it's going to go up or down, then put the friction in and draw the diagram and look at the pieces. If you have to individually, numerically solve those, do that. And then say, this is the uphill force, this is the downhill force. Uphill force wins, it's not going to move. Or something like that. We'll go through 27 in detail on Monday. I might even make a video of it, because I can get another one of these to take home.
You might stop.
What? Oh yeah, I do want to stop this.
So